Hey, how's everyone doing today? Hang on, let me turn this off. Good, nice. So I just checked the syllabus page, and I swear I updated it to have the link to the YouTube, but I'm not seeing it there. Am I crazy, or has that never been there? You don't? Okay, I don't know what's up with that, but let me go ahead and add it. Maybe I just didn't click save. Let me do that real quick. I must not have clicked save or something. That's bizarre. Okay, well, it should be updated now. Yeah. Weird. Okay, I don't know what that was all about, but sorry about that. Very strange. Yeah. So yeah, I'll be posting the lectures there as soon as they finish processing in the cloud and I can download them, etc. And for some reason, the algorithm loves to pick like the most ridiculous moments of lecture of the video for the thumbnail. So for one of them, I'm making like the aliens face. I don't know why, and they were all like equally terrible too. So I guess that's what we're gonna have to live with. But yeah. Okay. Yeah. Also, yeah. If you also didn't know, you can also have access to the recordings on the Zoom tab, but the YouTube I figured would be a little more convenient. Okay. All right. So incredibly, I still did not finish 12 yesterday, so let's finish that up. And by the way, if you have not already, you need to sign up for Achieve ASAP. I'm gonna have the first learning curve due probably Sunday. I'll give people a little bit of time to join, but if you haven't joined, if you haven't accessed it yet, you need to do so like as soon as possible. You can, there's a 14-day free trial, I believe, for this class. I would go ahead and do that just to be on the safe side. And then you can, pay later if you need to, but please get on Achieve as soon as possible. Does anyone have any trouble with that, or? All right, cool. Well, please get on that. All right. So we're going to finish up 12.1, and then we'll start talking about 12.2. So vectors in the plane. Okay. All right. So so let's look at unit vectors. So we said vectors have two properties, right? They have a direction, unless you're the zero vector, and you have a magnitude, or you can also think of it as a length. So unit vectors are going to be very convenient. We'll use them a lot, but unit vectors are just, unit means one, right? So unit vector is just all vectors of magnitude 1. So let me say a vector v is a unit vector if the magnitude of that vector is 1. So for a lot of formulas and stuff, it's very convenient to talk about unit vectors. And often we don't care so much about the magnitude of the vector. We mostly, for some aspect, or for some applications, we just care about the direction it's pointing in, right? So in that case, often it's useful to use a unit vector. We don't care about the magnitude, so let's just say it's magnitude 1, and we just care about the direction it's pointing in sometimes. So every vector, except the 0 vector, has a direction, right? So we can talk about the vector which points in the same direction as a given vector, but has magnitude 1. That's often very useful for a lot of formulas. So if you have some non-zero vector, something that's not the 0 vector, it has a defined direction. And we can talk about the unit vector pointing in the same direction. So basically, we just take that vector, we scale it. How do you scale a vector? What do you do to the vector?
Lambda.
I couldn't understand you there, but we multiply it by a scalar. So we need to multiply this vector by a scalar. If we want it to point in the same direction, we want it to be a positive scalar. If it's a negative scalar, remember it points in the opposite direction. So we need to find a scalar to multiply it by. Well, it's very simple, in fact, what we do. So the unit vector, so the vector of length 1, which points in the same direction. So the unit vector pointing in the direction of v. So this book calls it E. E is pretty common to use for just an unspecified unit vector. So E sub v means E is common for a unit vector. So it's a unit vector pointing in the direction of v. So basically, you just take your vector v and you multiply it by the scalar 1 over the magnitude of v. So if you like, you can check that that's a unit vector. So remember, this is a useful thing to remember. But if you multiply a vector by a scalar lambda, then the magnitude of lambda times the vector is just the absolute value of lambda times the magnitude of the vector v, right? So then the magnitude of 1 over the magnitude of v, and remember the magnitude of v is the same as the length. Length is always positive, times v is, well, the absolute value of 1 over the magnitude of lambda is just 1 over the magnitude of lambda because it's positive. So 1 over the magnitude of v, my bad, times the magnitude of v, which is of course 1. You don't need to remember that, but this is a useful thing to remember here. But this is a formula you'll be using over and over, and that's an important thing to remember. So if you want to take a vector and turn it into a unit vector pointing in the same direction, you just divide by the magnitude. Okay. A useful, so this is kind of an obvious thing to write, but it's a useful way of thinking about vectors in certain situations. So turns it into a unit vector, divide the vector by the magnitude, right? Multiply it by 1 over the magnitude Same as dividing by the magnitude. Yes, correct. Oh, sorry. Okay, so often we can think of a vector as in the following way. Okay, this is really obvious, right? You multiply by the magnitude v, you divide by the magnitude of v, the two cancel out, and you get the vector v. But a useful way of thinking about a vector is as the magnitude of your vector times the unit vector pointing in the direction of your vector. So think of a vector, any vector v you can write as the magnitude of that vector times the unit vector pointing in the direction of the vector you want. Does that make sense? And here's a kind of situation where that comes in handy. And these types of questions pop up all the time on exams. So for instance, suppose we have some vector. So we have a vector, sorry. We want to find a vector, and we just know the direction and the length, right? So find the vector of length 4 E sub v is the unit vector in the direction of v. So the direction, the vector which has length 1, which points in the direction of v. So pointing in the direction of the vector 3, 5. Okay, so to do this, we're going to use this way of thinking about a vector. All we know about our vector is the magnitude. We know it has magnitude 4. And we know the direction it points in, 3, 5. Is 3, 5 a unit vector? No, it doesn't. But we can turn it into a unit vector by dividing by the magnitude. What's the magnitude of 3, 5?
Square root of 34.
Right. It's the square root of the sum of the components squared, square root of 9 plus 25, and square root of 34. So we know the vector we want is going to be the magnitude, the length, 4, times the unit vector pointing in the direction. Well, we know 3, 5, we turn it into unit vector. So that's 1 over the magnitude of 3, 5, which is 34, times the vector 3, 5. So we get 4 over root 34 times the vector 3, 5, which is a perfectly fine way to write this vector. On an exam, that's totally fine. But if you had something like multiple choice, often they'll bring the scalar inside. Remember, when you multiply a vector by a scalar, you multiply all the components by that scalar. So we get 4 over root 34 times 3, which is 12 over root 34. And then 4 over root 34 times 5, which is 20 over root 34. Both of those are perfectly fine. But that's the vector we're looking for. So you can think of a vector as the magnitude of vector times the unit vector pointing in the direction of your vector. Okay. And one last thing I want to mention is there are two very important unit vectors in R2. And these are called the standard basis unit vectors. So if you've taken 220, you know a basis means you can write all of your vectors in terms of these two vectors. And they're unit vectors. They have magnitude 1. And those are the vectors I, which is the vector 1, 0. They're so important we give them their own names. And j, which is the vector 0, 1. So I don't want to dwell too long on these because they're very simple. We're going to see them over and over and you'll get the hang of them. But the reason we like these is because you can really easily write any vector you want in terms of I and j, right? Right. So if you have the vector AB, well, you could just write that as, we'll break it down like step by step here. The vector A0 plus the vector 0b. Right, does everyone agree A0 plus 0b is AB? You're just adding component by component, remember? And then we can pull out the A out of the first one, and we get A times 1, 0, and B out of the second one, and we get B times 0, 1, which is, of course, 1, 0 is I, so that's just A times I plus B times J. So you'll often see the vector A0 written like this. And so whatever you're multiplying by I is the first component of your vector, for the X component. And whatever you multiply by J, let me make that more clear what I'm pointing to there. Whatever you're multiplying by J is going to be the Y component. And we'll kind of use this interchangeably, right? Go away, dude. Why do you like this? Okay, lovely. So just keep that in mind. So like sometimes rather than writing like the vector 3, 4, what is going on, man? That's better. Okay. So instead of like writing the vector 3, 4, I might just write 3i plus 4j. So just know that those two things are interchangeable. They mean the same thing. Oh, sorry. And one last thing. Forgot to mention this. This might show up on the homework. So if we're looking at all the vectors of length 1, there's another way we can think of them. So if we start all these vectors at the origin, if you look at all the vectors which have length 1, well, if it starts at the origin, if the tail's at the origin, the tip is going to be length 1 away. The set of all points distance 1 away from the origin is the unit circle, right? Let me do a different one. So suppose we look at this vector here. We can characterize our vector with the angle it makes measured counterclockwise with the positive x-axis. So if we start this vector at the origin, it makes angle theta measured counterclockwise with the positive x-axis. And remember from trig, that means our endpoint here is the x coordinate is going to be cos theta, the y coordinate is going to be sine theta. So that means that if your vector makes angle theta with a positive x-axis, your vector is going to be cos theta sine theta. We don't use this too often. We'll talk more about angles later, but that's a useful way to think of some unit vectors. All your unit vectors you can write like this. And that's all I want to say about that. But any questions about 12.1? Okay, so let's move on to 12.2. And we're going to start talking about R3 space, which is where we're going to spend most of our time in this class. You're already nice and familiar with the plane. But in here, we're mostly going to be dealing with R3 space. So three-dimensional space. In here, we're going to write that as R3. Right, that's because it's 3 copies of the real line. And you can write each point as how far along the first copy, the x-axis, you go, how far along the second copy you go, the y-axis, and how far along the z-axis you go. But now, so we don't really think about it too much in R2, but we always draw R2 with the y-axis pointing up, the positive y-axis pointing up, and the positive x-axis pointing to the right. You don't have to draw it like that. If you want, you could do something like the y-axis pointing, positive y-axis pointing down and the positive x-axis pointing to the left. I don't know why you'd want to do that. But these two are essentially the same thing. It's just you've taken this one and you've rotated it by 180 degrees. But right, you can take this first one and you can rotate it onto the second one and you get the same thing. However, if I switch the positive x and y axes, if I said, now this is the positive x-axis and this is the positive y-axis, there's no way I can take this first copy and rotate it so that it fits on, it maps onto the second copy, right? I can't rotate it so that the positive x-axis matches the positive x-axis on here, and the positive y-axis matches the positive y-axis. If I match with the positive x-axis, the y-axes are pointing in opposite directions. So we say these two things have different orientations, right? So there are two orientations of R2 corresponding to those two things. And similarly, there are two orientations of R3. And I won't get too much into it, but we want to make sure we're always using a certain orientation of R3. So whoops. The way we can remember, this is almost never going to be an issue because we're almost always going to draw R3 in the same way. But the way you can remember how to orient the axes is as follows. So usually we draw R3 like this. the z-axis, the positive z-axis pointing up, the positive y-axis pointing to the right, and the positive x-axis is coming into the page, right, towards you. Or sorry, coming out of the page towards you. But we could draw the axes in a different manner and still have the same orientation. But we're going to use the right-hand rule. So since this is not super important, I'm just going to, can everyone can see me right now, right? Moving around.
Yeah.
So the right-hand rule is basically, I'll just describe it in words because it's easier than writing it down. Basically, you orient your right hand so that your fingers sweep inward from the direction of the positive x-axis towards the direction of the positive y-axis. So I start my fingers in the direction of the positive x-axis, and I want to orient my hands so that I can move them inwards towards the direction of the positive y-axis. So in this case, so my fingers are pointing towards me, that's where the x-axis is, and I'm curling them inwards so they go to the right towards the positive y-axis. Your thumb is going to point in the direction of the positive z-axis. So if you orient your hand so that you can start at the positive x, sweep inwards towards the positive y, your thumb will point in the direction of positive z. So I'll just do one example. So suppose I said this is x, positive x, and this is positive y. Actually, let me draw a better picture than that. Okay, so the positive x-axis points to the right, the positive y-axis points up. Does the positive z-axis come out of the page towards you, or does it go into the page away from you? So orient your hand. Okay, I start at positive x, I sweep in towards positive y. Is your thumb pointing towards you or away from you? It's pointing towards you, right? Sometimes it's kind of hard to orient your hand that way, but this is, in fact, the positive z-axis. But for instance, if I switched these two, if I said, now this is the positive x-axis, this is the positive y-axis, then I would have to move my hand in the opposite way, start at x, sweep in towards y. Now my thumb is pointing away from me. So the positive z-axis would be this way. But like I said, I don't want to dwell on this too long, but that's our rule for the orientation of R3. Not going to worry about that too much. This is almost always how we're going to draw R3 though. Z up, Y to the right, X coming out of the page towards you. Okay. So the setup points, obviously, are going to be the same way. It's going to be ordered triples. We have a point ABC. So that means we go A along the x-axis. Let me say B along the y-axis. And C along the z-axis. That's a really awful picture. Get used to terrible pictures, I guess. There are better pictures in the book. But I'm sure you all know how coordinates work in R3. And so we have three especially important planes which lie inside of R3. Right, so if you have z going up, y going to the right, and x coming towards you, if you think about it as like looking into a corner, so then the floor is a plane extending out in all directions, and the floor is the xy plane, the plane which contains the x and y axes. So the wall in front of you contains the y and z axes. That's the yz plane, of course. And the wall to your left contains the x and z axes. That is the xz plane. So those are our coordinate planes. So it's going to be useful to refer to them using an equation and not by as the xy, yz, and xz planes. So all of the xz, everything, let's look at the xy plane, the floor. So if you think of z as height of a point, right, the z coordinate, what do all the points in the xy plane have in common? What is their z coordinate? Right, it's everything in the xy plane has z equals 0. And in fact, all the points with z equals 0 lie in the xy plane. So the xy plane has the equation z equals 0, right? If you look at all the points x, y, z, where the z coordinate is 0, well, that's the xy plane. Similarly, the xz plane, what equation describes all those points? What do all those points have in common? Right, that is y equals 0 is the xz plane. And then similarly, the yz plane is the plane x equals 0. So those are the three coordinate planes, x equals 0, y equals 0, z equals 0. And we'll come back to those over and over and over again. So similarly, so in R2, right, the coordinate axes split up the plane into 4 quadrants, right? So it's like 1, 2, 3, 4. I don't remember the order. All we care about really is the first quadrant is where x and y are positive. Similarly, in R3, if you look at the coordinate planes, they split space up into 8 octants. Similarly, don't care about any of them except for the first. The first octant is where x, y, and z are all positive. So it's a set of points such that, I write ST a lot to stand for such that. Such that all the coordinates are positive. X, y, and z are all positive. So that's the first octant. Okay. So how do we measure distance in R3? Well, it's exactly the same as in R2, except now we have a third coordinate, a third dimension that we have to take into account. So if your point P is, say, A1, B1, C1, and your point Q is A2, B2, C2. The distance from your 2 points is you look at each of the coordinates, look at the difference, you square it, and then you add them up and take the square root. So the difference in the first coordinate is A2 minus A1. Square it. Difference in the second is B2 minus B1. Square it. Difference in the third, C2 minus C1. Square it. Add them all up, take the square root. So exactly the same as in R2, except now we have the third coordinate to deal with. Okay, sorry, moving really quickly here because I have a little bit more I want to get through. So let's look at a few really basic surfaces. In R3. So the simplest kind of surfaces we have in R3 are going to be planes. We'll talk more about planes later, but there's some very simple planes, or they're all simple, but some certain planes with very simple equations that we can talk about right away. So we already saw 3 planes, the coordinate planes, x equals 0, y equals 0, z equals 0. So we saw the xy plane is the set of all points whose z coordinate is 0. The xy plane is the plane z equals 0. Well, suppose we want to consider a plane parallel to the xy plane, but say we lift it up by 4, right? So instead of the set of all points whose z coordinate is 0, we look at the set of all points whose z coordinate is 4. Right, that's obviously the plane z equals 4. And it's going to be parallel to the plane z equals 0. Also known as the xy plane. So the plane z equals 4 is just, it's parallel to the xy plane, the plane z equals 0. But now it's a set of all points which go, which have z coordinate 4. Similarly, we can do the same with the other 2 axes. So the xz plane, we said was the plane y equals 0. Well, if we look at, say, y equals 2, that's going to be a plane parallel to the xz plane, the plane y equals 0. And then similarly, you could do like the plane, say x equals -3. That is something special. No. Sorry. There we go. Go back to the last slide. Sure. And so planes of the form x equals a number, y equals a constant, z equals a constant. Those are all parallel to coordinate planes. Okay. Let's quickly look at the equations of spheres. Okay, so in R2, a circle centered at a point of radius, say r, is, you can describe that in words as a set of all points, distance r away from your point AB. So if here's your center, there's your radius. If we look at the circle centered at AB of radius r, really beautiful picture. It's going to be the set of all points, distance r away from AB. That's your circle centered at AB of radius r. Similarly, in R3, if we look at the set of all points, which are distance r away from a given point ABC, you have a sphere. Let me do this without drawing this. So we have a point ABC. And we look at the set of all points of distance r away from that center, ABC. You have the sphere of radius r centered at ABC. So the sphere is a set of all points, distance r away from a given point. So we're going to use the distance formula to derive the equation of the sphere. So the sphere of radius r centered at the point ABC So we want an equation describing all these points. X, Y, Z is on a sphere if it satisfies this equation. So the set of points X, Y, Z which are distance r away from ABC. So in other words, the distance r, or let me write it this way, the distance between the point X, Y, Z and ABC is square root x minus a squared, right? The distance in the x coordinates, then the distance in the y coordinates squared, so y minus b squared, and the difference in the z coordinates, c minus z squared. So that's the distance between x, y, z and ABC, and we know that's got to be equal to r. So that's perfectly fine, but usually we like to square both sides, usually for calculus reasons, but as we'll see later. So let's square both sides. And when we do that, we get the equation. So the sphere is centered at ABC, a radius r, has equation x, we got rid of the square root because we squared both sides. So we have x minus a squared plus y minus b squared plus c minus z squared is equal to r squared. Oh, I said it's, oh, it actually doesn't matter because we're squaring it, but yeah, sorry, I don't know why I wrote it in that order. I'll just do it for z minus c squared. Yes, you're correct. They're the same thing though, but yeah. So ABC tells us our center. Notice it's minus a minus b minus c. And then the right-hand side is the square of the radius. Oh. Okay, so let me give you an equation, which doesn't look like, this is sort of the standard form, but this is not the only way you could write the equation of a sphere. So let's show that the equation, say x squared plus 2x plus y squared minus 4y plus c squared equals so let me see. Let's say 11. So this doesn't look like the equation we have up there. But what we're going to do is we're going to manipulate this so that it is in this standard form that we just showed up here. And we're going to find the center, and we're going to find the radius. Okay. So let me rewrite our equation. So we had x squared plus 2x plus y squared minus 4y plus c squared equals 11. Okay. So we don't want the x, y, or z terms by themselves, because in our standard form, all we had was x minus something squared, y minus something squared, z minus something squared. So instead of x squared plus 2x, we want to write it as x plus something or x minus something squared. So let's see if we can get that in that form. So we're going to complete the square, if you remember how to do that. I will quickly remind you how to do that. Okay, so if I want to have a perfect square, if I want to write x squared plus 2x plus something as x plus something squared, what do I need to add to this? Not quite. I think you have the right idea, but you're going in the wrong direction. We need to add 1 to it, in fact. X squared plus 2x plus 1 is a perfect square. How do I write that as something squared? Right, it's x plus 1 squared. So the trick is you take your b here is, so it's x squared plus bx. So your b is positive 2 here. So you take half of that positive 2, and you square it, right? So half of that is 1. You square 1, you get 1. So that's what you need to add to get a perfect square. So we added 1 here, right, to the left-hand side. We also need to add 1 to the right-hand side. So that becomes x plus 1 squared, which is the form we wanted here. And to do that, we had to add 1 to the left-hand side. So we also need to add that to the right-hand side. Doing the same thing for y. So y squared minus 4y. Well, we want to make that a perfect square. So we take half of negative 4, negative 2, and we square it. And then we add that. So plus 4. Y squared minus 4y plus 4 is y minus 2 squared. We had to add 4 to the left-hand side. So we need to add 4 to the right-hand side as well to maintain equality. And then z squared, there's nothing to do there. You can just think of that as z minus 0 squared. Don't need to complete a square. It's already a perfect square. So nothing needs to be added there. So we have x plus 1 squared plus y minus 2 squared plus z squared, or I'll just write z minus 0 squared, is equal to 11 plus 1 plus 4. That is 16. So what is our center? And what is our radius? Center is what? Right, center is negative 1, positive 2, 0. Remember, it's minus a minus b minus c. So negative 1, 2, 0. That's really ugly. And our radius is the right-hand side is the square root of the right-hand side. So our radius is going to be 4. Let me at least pretend that is legible. Make an effort here. So negative 1, 2, 0, and our radius is 4. Okay. Any questions about anything today? If not, I'll go ahead and end it here. If you have not already, please go sign up for Achieve immediately. If you're having trouble, please shoot me an email. Your first, I'm going to assign the learning curve. That'll be due by the end of Sunday. It's a pretty quick assignment. And then the first homework will be due probably Thursday next week. But yes, if not, have a great day, and I will see you guys next week.
Thank you.